applied research and development on agroclimate, remote sensing, yield forecasting, drought monitoring, agriculture water balance, and land dynamics. She has 25 years of experience in applied science and research, monitoring environmental health, ecosystem, food productions, and food security using geospatial data. Her expertise spans remote sensing, land surface hydrology, soils and climatology of agricultural, forested, and industrial mines and metal environment. She has worked with a variety of remote sensing data, including hyperspectral, optical, active, and passive microwave at a variety of geographic scale. For the past 12 years, she has been leading the projects estimating risks to agriculture system from drought and excess moisture using earth observation, integrating this information into crop yield forecasting at regional and local spatial scale, forecasting drought, soil moisture, and agriculture water management, and building integrated modeling and data exploitation system for the National Agroclimate Information Service at Agriculture and Agri-Food Canada. So once again, Catherine, so over to you.
Okay, thank you. Sorry, I was late. I must have, the time I was sent didn't line up.
Okay.
Okay.
No issue. No issue.
Okay. All right. Share my screen here.
I'll be requesting all of you just unmute your system so we can hear properly.
Okay, I'm having trouble sharing the screen here. Okay, can you see the screen?
Yeah, it's coming. It's coming.
Okay.
Yeah, can you make a full screen? Yeah, okay, absolutely okay. Please proceed.
Okay. Well, thanks everybody. Okay, so I'm going to talk to you today about some work that I've been doing over the last few years, looking at applications of remote sensing for operational agrometeorological advisory services. So just a little bit of background about the agriculture and agri-food sector in Canada. It employs about 2 million people and is about 8% of our gross domestic product, and it's largely export focused with about $60 billion in exports per year. This green area that you can see on the map is what we call the agricultural extent of Canada. So this is the area that's climatologically suitable for agriculture. So you can see it's actually a fairly small part of Canada overall. But it is a large landmass despite that, and it's both the agriculture and the population is widely dispersed with a large variety of crops ranging from fruits and livestock to cereal crops to vegetables to maple syrup to honey to wine production. So there's a large variety of crops that vary geographically across the country. One thing that's somewhat unique in Canada is that it is largely weather driven, where there's very little irrigation in Canada. So the impact of weather and climate extremes is often results in billions of dollars of economic costs each year. And for that reason, our team works to try and provide the sector with information on how weather extremes are impacting agriculture. In terms of climate change, because of this vulnerability to weather and changing climate normals, it makes the sector vulnerable, but it also can bring to changes where things are grown, but also bring additional risks. And finally, climate change mitigation. So reducing emissions from nitrous oxide, methane, and sequestration of carbon in soils is an important part of our agricultural strategy each year. So as agriculture is both impacted by climate change, but also something that impacts climate change overall. So I'll just tell you a little bit about our team. I'm with the National Agroclimate Information Service, or NACE. So we're an applied science and operational delivery team providing tools to monitor the impacts of climate on agriculture. We undertake monitoring, early warning, using authoritative data sets and models to understand climate risks and impacts. We kind of focus across several main thematic activities, so mitigating and adapting to climate change, increasing the resilience of agroecosystems, and accelerating digital transformation. And then across our team, we work in applied science and innovation, the development and application of geospatial and analytical tools, providing expert analysis and interpretation to various partners in the sector, and building collaborations and partners to expand the range of work that we can do. And I just provided a link at the bottom to our website. We have a website where almost all of our data products are made available. So I'll talk to you today about some of the key activities we do. We have activities that we refer to as our operational activities. So these are things that are, the models are well developed, well validated, and they're running on a regular basis, ranging from drought monitoring to crop yield forecasting to climate risk assessment to remote sensing based products. And then we have some activities that are a bit more in the research and development phase in terms of developing new indicators, new types of forecasts, new types of higher resolution modeling, and migrating some of these activities to high computing environments to exploit big data. So at the base of all of our activities is geospatial information about the agriculture sector. And we kind of have four main data sets or categories of data sets that we rely on. One of the underlying is just traditional surveys and more recently crowdsourcing. So these are questionnaires ranging from our annual census that's conducted by our statistical agency to windshield surveys of crop type and crop condition and other field data collection, as well as crowdsourcing. We have an application that farmers can upload weather conditions impacting their agricultural activities. Another traditional source of information is climate stations, monitoring stations. We use both automated weather stations and Doppler radars that are located across the country. What I'm going to talk to you mostly about today is the work that we're doing with satellite remote sensing. We use optical, thermal, radar, microwave, and gravity satellites, both polar orbiting and geostationary, and a wide range of resolutions ranging from less than a meter to greater than 10 kilometers. And we also combine these with a large number of models, both statistics and physics-based models to simulate information. And one of the unique things about that distinguishes us from meteorological agencies is we aren't just looking forward, we are often looking backwards. So many agroclimate services rely on using both current data and historical data to determine the normals and risk conditions that are falling outside of what is normally collected. And for this reason, we really need long-term consistent data records to observe these types of changes. I'll just talk a little bit about some of the information sources that we use. So surveys, I mentioned, these are some examples from our annual census. So this particular example is looking at farms with maple syrup production in Canada. We work with our prairie pest monitoring network, who do prediction of pest populations. They combine this with field surveys and climate data to estimate growth stage of different pest populations across the country. And then in this top corner here is an example from our crowdsourcing activity. So this is farmers reporting climate impacts on feed availability. So we're in areas you see red, there's extreme impacts reported by the farmers, and ranging down from the orange and yellow to no impacts at all. In terms of our station-based data, we operate a kind of a network of networks across the country. So you can see this map here. All these green dots are the meteorological stations that we use, mostly precipitation and temperature data. And then the map on the bottom of the screen is the location of our Doppler radar stations, and then the range of sensitivity that they have. So you can see these are concentrated along the southern border of Canada, which is largely where all the agriculture in Canada is. So this is a good source of information from us. So we collect data from both our federal monitoring agency, which is Environment and Climate Change Canada, but we also collect data from provincial government agencies in different provinces, as well as volunteer networks. So the Community Collaborative Rain, Hail, and Snow Network, which is a initiative started in the United States, also has a presence in Canada. We have about 420 of those reporters across the country that are collecting rainfall data. We use all of these data sets to produce daily maps of agroclimate conditions. So here's some examples that come out of our station-based network. Things from ranging from precipitation percentiles, the number of days with hot temperatures, so in this case temperatures above 30 degrees, soil moisture anomalies related to drought modeling, standardized precipitation index. So we do a daily quality control of all the weather stations in our fully automated system. We use both current data, station quality rankings, and historical gridded data to produce these gap-filled time series to estimate a large number of agroclimate measures. And we produce a number of indicators, so precipitation, accumulation percentiles over different time periods, temperatures, heat waves, crop heat units, as well as a number of drought indicators, such as the Palmer hydrological drought index. We do modeled soil moisture, as well as standardized precipitation and evapotranspiration indices. So as you can see from our maps here, we have a large number of stations concentrated in the southern parts of the country. But as you get sort of outside of that agricultural region of the country, the stations are much more sparse. And there's a lot of gaps in different provinces that have different densities of stations. So one of the reasons we look to remote sensing is to really fill those spatial gaps of what we can't get from more traditional monitoring networks. For that reason, we've been in the last 20 years been looking more at remote sensing as a source of data. When you look at remote sensing, and this figure on the bottom is an example that I put together with some colleagues in the United States, looking at different data types at different spatial resolutions and from different frequencies. So we have everything from microwave data. There we go. We have microwave-based indices. We have optically based indices from what we call moderate resolution satellites, where you get sort of a synoptic view of an entire state, in this case, California. And then you have what we call higher resolution, so things like Sentinel, Landsat, airborne drone type sensors that you can get right down to very minute details within a field. And then when we look at the electromagnetic spectrum, so different sensors detect information at different parts of the electromagnetic spectrum. We have optical data, which is collecting in the visible and near infrared. And for that, the optimal things that you can get from that are things like crop health, leaf area index, crop residue cover, crop types, crop growth stage. When you look at radar, so these are active sensors that send the optical sensors are using reflected energy from the sun. Radar data send their own pulse of energy at microwave frequencies to the surface and measure the returned backscatter. Now, for those types of sensors, they're more sensitive to things like dielectric properties of the surface, which makes it an ideal tool for looking at things like soil moisture or surface hydrology. But it's also sensitive to things like volume scattering, which gives you information on plant structure, crop biomass, as well as surface roughness, from which you can infer tillage. We also use passive microwave sensors. So these are sensors that are measuring naturally emitted microwave from the surface. This is an example of that right here. So you can see that they're much coarser resolution because the amount of energy that's being released is much lower, but you do get very frequent measures from daily to every couple of days, timescales of the entire Earth. So from those, we can get things like soil moisture and vegetation water content. And finally, thermal, which is also measuring emitted energy. We can get things like temperature and evapotranspiration. So I'll give you some examples of how we're using each of these types of technologies in our monitoring. And finally, models. We use these often on their own and often in combination with different remote sensing data types. We use both statistical, empirical methods, more often machine learning, artificial intelligence, which are learning models that are somewhat more advanced, statistical learning models, as well as physical or process-based. So these can range from very complex models that model all parts of the physical environment to very simple models of looking at water balances, as well as crop models that do much more detailed estimation of crop growth and crop vigor. So I'll spend the most of the rest of the talk talking about Earth observation and how we're using it. So I'm going to start with what I think most people are probably familiar with. There are just your standard vegetation indices. We make heavy use of synoptic measurements of normalized difference vegetation index and other similar indices, which use band ratios to quantify differences between red and near infrared surface reflectance to monitor plant health at multiple scales. So this is an example of maps that we produce every year. It's cycling through, if you can see it. These are actually maximum 7-day NDVI composites of the entire country from the MODIS sensor, and it's comparing current conditions to the long-term average. So where plants are doing better or have higher greenness than average, these are showing up in green, normal showing up in yellow, and then areas that are under stress are showing up in red. We use long-term data. One of the ideal qualities of using a sensor like MODIS or other moderate resolution sensors, such as the advanced high-resolution radiometer or AVHRR and now VIIRS, are that these data sets are often intercalibrated or have long-term sensor records, so we can look at the changes over many, many years. And we use this data to derive a number of more higher information products. So that one's just a simple band ratio that we saw in the previous, but we can take this information and convert it into other types of indicators. So this is an example from our Vegetation Drought Response Index. This is an index that we developed in partnership with the Drought Mitigation Center in the United States. This combines time series, satellite NDVI, and station-based drought indicators, such as the standardized precipitation index and other biophysical data, such as land cover, irrigation, and ecozones to model drought severity at a pixel scale. So you can drill right into this, and this is giving you 1 kilometer resolution of drought stress. This is an example from just last week here in Canada in our prairie provinces. So you can see there's a high degree of drought stress, especially in the western prairies right now. Another more advanced method that can be taken from optical satellite data is looking directly at leaf area index. We've been doing a large number of work in the last few years doing leaf area index retrieval from Sentinel-2 optical satellite constellation out of Europe, using the SNAP toolbox calculate leaf area index. So this graph on the over here, you can see is the correlation between satellite LAI and LAI measured on the ground with an optical instrument. So we're getting very, very good correspondence using this model. This tool has actually been recently translated for Google Earth Engine by our colleague at Natural Resources Canada, the Leaf Toolbox. There's a link to the GitHub page there where you can download that toolbox. And we're working on a pilot right now to run this for all agricultural regions of Canada. So this gives you very, very high resolution data. The data that we looked at in the previous slides was at sort of 200 meter to 1 kilometer resolution. This is, we're getting more 20 meters, so we can see directly what's happening in individual fields. And this graph over here, you can see the changes in LAI over a growing season for a number of different fields at our research site. Seasonal greenness, so this is another derived product from seasonal NDVI. So you can see in the bottom corner here, we have our NDVI values as they evolve over a growing season. So they're low in the spring, they hit a peak at peak vegetative growth, and then they decline. We've implemented a model to calculate these inflection points at both ends of what we call the start and end of season, and then do a model, a fit to the observed satellite data to calculate this area under the curve, which we call the seasonal greenness. This indicator is a bit more comprehensive than using NDVI alone, as it changes in this curve over the season in terms of either the peak value, but also the shape of the curve that can happen as a result of stress, show up differently. And this makes it a good predictor of crop yield, as well as other kind of stresses on the thing. And you can see that we also piloted calculating this in a platform such as Google Earth Engine, where we can roll it out over large areas of the country very quickly. We can also use this type of model for estimating things like growth stage. So as I mentioned in the previous slide, in order to calculate this seasonal greenness, we need to calculate these inflection points in our NDVI curve, which we named the start of season and the end of season. And this is an example of this being calculated with the different colors representing different dates. You can see as we go from south to north through the United States and into Canada, we're getting later dates of that start of season. We've done a lot of analysis of using this directly to estimate the growth stage. And within most regions, we were able to estimate the seeding date within 8 days or less using the remote sensing data alone. We've been doing some work to look at combining this with more traditional bioclimatological models. So this is an example showing different estimates of growth stages with different biometeorological models. And this map here is just showing the correlation between using the remote sensing based method as well as the heat unit based method to estimate. So there's a fair bit of difference, but I think there's a lot of potential to combine these two to get better estimates of growth stages, and I'll talk a little bit more about that later. When we get into microwave sensors, so we also make a heavy use of passive microwave satellite soil moisture. In the last decades, there's been an increase in the availability and the sophistication of these data sets. We make heavy use of the Soil Moisture and Ocean Salinity Mission, or SMOS, from the European Space Agency that was launched in 2009, as well as the SMAP sensor that was launched by NASA in 2012. We calculate different anomalies, soil moisture anomalies. So this isn't actually showing, these maps are not showing the soil moisture, but the soil moisture difference from the long-term average. Again, this is why we need long-term climate records to characterize these things. But what you can see in red are areas where conditions are much drier than normal, and then the blue areas representing areas that are much wetter than normal. These sensors are only sensitive to surface soil moisture, which makes it a little bit more of a challenge to use when we're looking at agricultural crops. So as I mentioned, in the last few years, there's been an emergence of many different satellite soil moisture data sets that enable us to use these in more of an operational context. So I mentioned the SMOS mission launched in 2009. The SMAP mission was launched in 2015. It has a similar L-band radiometer on it. It did have a radar instrument, but that instrument's no longer functioning, as well as an initiative from from Europe, combining different passive microwave satellites to create a long-term data set going back to 1979. We're largely using the data between 1992 and 2018. So this is a blend of active and passive microwave satellite soil moisture data sets. This isn't released in real time, but it's provided as a normal that's updated every year. I should have updated the year because it's updated until last year. So when you look at satellite soil moisture versus in situ, because we're only looking at the surface with a satellite, we do need to treat the data a little bit differently. So these solid lines that you see are looking at in situ measured soil moisture over a growing season at a 5 centimeter, 20 centimeter, and 75 to 100 centimeter depths. So you can see that the correspondence is a lot higher with the surface soil moisture than it is with the others. And you can see that there's, when you look at the surface, you're seeing these wetting and drying cycles. You see these a little bit as you get into what we might call the root zone. But when you get further down, we're not seeing as much dynamism in the soil moisture, which we're seeing with the surface levels. And we're really getting kind of a change in the baseline, which the satellites don't always do a very good job of capturing. So how are we using this data? We use it heavily in our climate-related production risk monitoring. One thing that, because we're looking at the surface, is a very good tool for looking at things like excess moisture at the surface. This is a report that we put out every couple of weeks during the growing season, looking at different provinces across the country and giving early warning of things like flooding, heat, rain, high winds, drought that are updated each week. So this is an example from 2014 where there was a huge rainfall event that affected an area between Manitoba and Saskatchewan. This is what it looked from our precipitation map. This is what it looked like on the ground. And this is what we're seeing from our satellite data. So we're getting a somewhat more spatially different picture than we can get from station data alone. When we look at how good our soil moisture data is at sort of identifying these moisture-related risks, we broke down, this is some work we did a few years ago, looking at all of these risks. So you can see that the sort of average conditions of our soil moisture data are corresponding fairly well with drought. It's wetter than normal when we have things like excess moisture and flooding, and that our risk is actually pretty close to the average. Slightly less good results using SMOS than SMAP, but still fairly similar. One of the challenges that we always face with satellite data sets is that because we're trying to estimate extremes, we need this distribution in order to verify that these extreme conditions are occurring. Because of the way that satellite data sets are calibrated, it's difficult to use absolute values to identify extremes. You often have to use them relative to the baseline of that particular data set. So what we often face with new satellite missions is having a sufficient data record in order to classify what is normal. So these initiatives that combine historical data sets together to create long-term records are very important when it comes to that. When we look at drought, it's a little bit more challenging than looking at excess moisture. Because surface soil moisture is very responsive to temperature, precipitation, it can be less indicative of long-term water storage. So where we're looking at to improve our drought monitoring is looking at a couple of things. So assimilating it into models, which I'll talk a little bit more later. Right now, the limitation of those is the models are actually not very good. And when we do the assimilation, the soil moisture is either heavily driven by the model or heavily driven by the satellite, depending on how the model is configured, which makes it difficult to discern different information than we're getting from the satellite data alone. Also, when we look at different, one way we can also overcome this is looking at these anomalies over different time scales to capture what we call kind of memory. So these maps on the side here are showing a 2-week anomaly versus a monthly anomaly versus a seasonal anomaly. And when you start to look at that, you can see that areas that have been consistently dry for a long period of time, which helps us better identify where droughts are occurring. So how many years of data do we really need to characterize that baseline for capturing these anomalous conditions? We did some analysis of looking at this graph here is how we characterize different risk conditions using a 27-year data set versus an 8-year data set. So you can see we have a much stronger difference between wet and dry extremes when we have 27 years of data. This is showing some frequency distributions of the soil moisture using different baselines of data. So we did some assessment, a leave one out analysis to look at just how many years of data do we need to really capture what we would get with a 27-year baseline. And we focused exclusively on yield. For determining low yielding years, which is normally what we're more interested in, we need about 12 years of data. Determining anomalously high yielding years is a little bit harder. We needed about 18 years to do that. But I guess the verdict is that the longer the baseline, the better. But we can get away with a shorter baseline as long as it's sort of greater than 10 years. Excess moisture, we can definitely see excess moisture, but when we try to sort of translate that into insurance, things that are useful for insurance, like too wet to seed, it becomes a bit more complicated because often land that is left fallow because it is too wet to seed in the spring, the moisture conditions are quite different. So this these graphs here are showing 3 different growing seasons where there was a large amount of excess moisture that led to failed seeding operations in the spring. And you can see the moisture conditions were quite different each of those years. So coming up with a predictive model has always been a challenge. We have been working on different predictive models. We're not convinced that the satellite soil moisture that we have right now is high enough resolution for really capturing these, because the factors that are driving most of these things are things like elevation and slope and the land cover and soil water holding capacity of the area. So this is something that we're still working on. When we look at drought, again, we have we've done some analysis of looking at satellite soil moisture kind of accumulated drought index versus more traditional station-based index, and we found that what we're capturing with our satellite soil moisture is really things like changes in evaporative demand rather than long-term soil moisture shortages, which is not surprising given that we're primarily looking at the surface. Well, although we can capture drought, so this is from a drought event in 2015, the soil moisture conditions were consistently below normal throughout the season when the drought were occurring, with some rainfall events later in the season. So we are capturing that, but the intensity of the drought is a little bit more difficult. So to say that in short, we can capture drought, not drought, but capturing intensity is a little bit more difficult with this type of data set. I'm finally looking at yield. We've looked at how satellite soil moisture can be used for estimating yield. Low yields are often associated with high spring moisture, not surprisingly, and low moisture during the growing season to a certain extent. So we want enough moisture during the growing season to support the crop growth, but not too much. So this makes it a little bit complicated. But this is showing the relationship between yield and satellite soil moisture at different times of year. So you can see there's a fairly good relationship there, and we have a paper that was released a few years ago talking about that in more detail. When we move to thermal data, we don't do a lot of processing of thermal data ourselves, but we're making use of some products that are available in the community. The evaporative stress index is one that we use quite a bit. This is based on combining thermal and optical data from MODIS in a model to produce evapotranspiration anomalies. So what you're seeing here are, with the very high stress, are evapotranspiration rates that are higher, are very high compared to the potential rate, and and where we're getting to low stresses, there's no water limitation on evapotranspiration. This is a product that's produced from some science developed by Martha Anderson at USDA and is produced operationally by NASA. So we've been using this data set a fair bit just for looking at in terms of moisture stress anomalies. So how are we using it? We use it for drought. So this graph over here is looking at this dark blue line is showing the change or the running average and change of evaporative stress index over the season. And this orange line here is showing changes in drought severity over time. So what we found when we did some digging on the data is that the evaporative stress fluctuates quite a bit in time with lows and highs with temperatures and low rainfall leading to dry periods. So we do need to to look at things that like drought, we need to look at moving averages. The temporal trend shows that higher evaporative stress during drought periods, in some cases, these high peaks in evaporative stress leading to more severe drought periods. So it's often more of an early warning sign than it is indicative of particular drought severity. We've also been looking at it and how we can use it for estimating crop yields. So these graphs are looking at the different colors or different geographic regions in Canada, and we've got kind of top five crops, field crops grown in Canada: barley, wheat, canola, soybean, and corn. And you can see this is the correlation coefficient between evaporative stress index and yield for these different regions. So you can see these little orange bars, which represent our prairie region. And we're seeing a fairly clear and consistent peak in correlation between evaporative stress index at sort of the end of season or peak growing season. This is probably not surprising. This is this area is our most water limited area in the country. And the index is much less relevant in maritime or coastal areas where water limitation is less of a driver of crop yields. Another tool that we use that we don't process ourselves, but we get from colleagues at NASA. So this is a total water storage data set from the NASA GRACE mission, or the Gravity Recovery and Climate Experiment. This is a constellation of 2 satellites that looks at changes in the gravitational field, which are sensitive to changes in large-scale hydrology. So we often use this as a proxy for groundwater. Again, this blue line here on the graph is the change in the GRACE total water storage over time, and this orange line here is the change in drought severity. And there's actually a very, very good correspondence there between these peaks and troughs in water storage and drought anomalies. So this is a very useful tool. It's very coarse spatial resolution, but it's very consistent with drought patterns. And finally, how do we integrate this data into models? So where remote sensing data is limited, we can use it to improve other types of data sets, such as models, to get information that we couldn't get otherwise. So this is the Canadian Land Data Assimilation System. This is a system developed by our colleagues at Environment and Climate Change Canada, and we've been working with them very closely over the last few years to make better use of the products that are coming out of that. So this is a land surface scheme that's integrated into their global circulation models. Their impetus for this was to provide improved meteorological forecast data, but we've been looking at how we can use it not just for forecasts, but actually for monitoring real-time conditions. So this is an example of modeled soil moisture integrating satellite data for North America. So this is giving us root zone soil moisture, so something we cannot get from satellite data alone. This is an example of just repeating our drought, our soil moisture anomaly product using surface soil moisture between just the satellite data alone and the satellite data combined with the model. So we can see somewhat different patterns, although the overall trend is fairly similar between the two maps. What's really valuable, though, coming out of this improved surface analysis of meteorological data is the numerical weather prediction data that's coming out of these systems. So one thing that we've been focusing on a lot recently is looking at what we call near-term forecast data analysis and reanalysis data. So we're looking at two products from our meteorological service, which are modeled weathered fields at the 10 kilometer and 2.5 kilometer resolution. So this is using their Kappa, or Canadian Precipitation Analysis product. And we've taken this and translated this into precipitation accumulation over the growing season. So you can see, this is a zoom in, you can see we're getting quite different spatial resolution of the information. And this is our traditional station-based maps. You see, we're also getting, we're capturing a lot of areas outside of the areas where we have the densest station network, which allows us to use this for a lot more complete analysis of what's going on across the country. We're combining this with a regional reanalysis data set that was also developed by our colleagues at the Meteorological Service of Canada. They recently produced a 39-year precipitation and ground surface reanalysis data set, which uses the ERA interim product from Europe to force the Canadian global environmental model at the surface and produce a number of observation fields. This allows us to, as I mentioned at the beginning, we often need not just current data, but historical data. So we now have a data set going from 1980 to 2018 for a large number of variables that we've been using as a historical baseline for some of these modeled weather data sets. We don't use just the near-term forecasts. We also use these improved forecasts for looking at things like monthly forecasts. This is an example of a product we have on our website called Extreme Weather Indicators. So these are a number of models that we use for our station-based data that we are now using on meteorological forecast data. We're using the 32-day forecast from the Global Ensemble Prediction System. These are updated daily and give lead forecast times for things like temperature, precipitation, heat, and wind at forecast scales of 1 to 4 weeks ahead of time. We're also using these types of forecast data for drought. So in Canada, Agriculture Canada has the lead for drought monitoring in Canada. So we produce the Canadian Drought Monitor, which is follows a similar methodology to the US Drought Monitor, if you're familiar with that. And we produce an integrated monthly product called the North American Drought Monitor with our partners in the United States and Mexico. This follows a percentile-based assessment of drought, with moderate drought being a 1 in 5 year event and exceptional drought being a 1 in 50 year event. This uses a convergence of evidence approach, which combines a large number of the indicators that I've talked about in my previous slides. And this has been running since 2003. Now that we have a number of years, we've actually used these data combined with our meteorological forecast data that I mentioned in previous slides to produce a drought forecast. So this is a relatively new product. This is our drought monitor from earlier this year, combined with the forecast for the following month. We use the same indicators that in calculated on the modeled weather data that we use in our drought monitor to separate both severity and presence and absence of drought. We've looked at how these drought indicators correspond with indicators at the station level. Generally, the temperature-based indices are quite good. The precipitation is more variable, which is why we use an ensemble system. So we actually produce 21 different forecasts of drought, and we use a probability model to determine how many of those models are predicting changes in drought status. Again, these are available on our website if you want to look at them. And we're using these forecasts as well as a number of our remote sensing data sets that I've talked about. This is some work that a student of mine, Jacob Mardian at the University of Guelph, is just finishing up to develop a higher resolution drought forecast. So he's been using an extreme gradient boosted decision tree model at 5 kilometer grid cells to predict the Canadian Drought Monitor categories. And there's a publication coming out on that. It's just in press right now. Finally, crop yield forecasting. This is another big activity that we do. This is largely based on remote sensing. Our current operational crop yield forecast, the Canadian crop yield forecasting system, combines satellite NDVI and climate-based indicators to predict crop yields for 60. I think we're at 16 crops right now, starting at the beginning of July. We use a large number of station-based data. We run these through a simple water budget model, the versatile soil moisture budget model, to produce a number of agricultural indices. And the model uses a robust regression model to predict drought in each census of agriculture region. So how does Earth observation fit into this? We've been using the NDVI for a large number of years in these models, but we've recently started integrating things like the evaporative stress index and the satellite soil moisture. This graph here is showing how many of the different regions that we predict yield for were improved by adding more remote sensing data. So the blue ones are ones that were improved by significantly by adding both the evaporative stress index and the soil moisture. The ones that are yellow stayed the same, and the ones that are green were better if we only used the NDVI data. Over here, you can see for different crops and for different regions, so Atlantic, Great Lakes, Prairie, Pacific. And these pink and purple and red bars are showing where improvements were made by integrating more remote sensing. So you can see there's a lot of geographic and crop type variability between how remote sensing data sets improve the prediction of crops. Generally, including these moisture-based satellite variables improved crop yield across most regions, particularly for canola, barley, and wheat. These are also largely grown in our most water-restricted region in the prairies, so that's probably not surprising. The soil moisture was often selected as a predictor over the NDVI in many of these areas. And it also often displaced weather-related variables, so things that we had been using from station-based indicators. So what that says is that these data sets can provide a proxy for more traditional meteorological information when we do crop yield forecasting. And we've more recently been looking at forecasting forages rather than just cereal crops. So we're working with some partners at the USDA on adapting their GrassCast model that they've been using in the Midwestern United States to produce a Canadian productivity forecast. So we've just recently completed developing all the model analysis. So this is a model that combines estimated actual evapotranspiration from a model with satellite-based NDVI and a correlation with biomass measurements made on the ground to provide an ensemble prediction of grass productivity over the growing season. So we're hoping to have something to roll out on this next year. And drilling down to more field scale is we've been looking at how to optimize crop models. So we talked about more synoptic scale models. We've also been looking at using gridded climate data, remotely sensed leaf area index, and surface soil moisture to optimize crop models. If you're familiar with using crop models, there's a large number of variables that need to be initialized in the model in order to get a good estimation of crop yield. So we've been looking at is trying to optimize the seeding date, the seeding density, the soil moisture, initial conditions, and the soil water content of field capacity for fields where we don't have any measurements of these using remote sensing. There's a paper that came out last year on this. With about some of the initial work was look at just adjusting these crop models in order to allow them to ingest satellite-based estimates. So this is some of the data sets that we're using. We're using 10 meter resolution leaf area index from Sentinel-2, which I talked about a little bit earlier, as well as 100 meter surface soil moisture. This is a product that we're getting from Vandersat, which is a company in the Netherlands, was recently acquired by Planet. And this is one of the products that they have made available for getting very high resolution soil moisture. We've looked at this soil moisture data set. It corresponds really, really well to our ground stations, which is a good start in order for bringing it into our models. There's still some biases that are a bit too high to distinguish between soil properties in very high pedodiversity regions, but we think that it'll give us a good estimation of those soil moisture initial conditions at the beginning of the season. We've also looked at how some of these other modeled weather data sets can be used. We've done some validation against ground measurements, looking at things like soil moisture, solar radiation, wind speed, relative humidity. And there's some biases in these data sets, but they are not bad, especially in areas where we have no data measured on the ground at all. And finally, we've looked at when we use those gridded data sets in our crop models, how does this bias our estimation of crop yields? So this here, you can see changes in LAI. The black line is using the weather station, and these dotted lines are using gridded data. So you can actually see this red line corresponds almost exactly to what the model is using from the station. So that's using only the precipitation. It seems there's a bias in the temperature data actually that's impacting our crop model. But the good news is that the precipitation is actually performing really well, because it's often the thing that we have the most trouble estimating when it comes to crop models, and the thing that is more spatially variable in time. So there's probably a potential to use a combination of station and remote sensing modeled based data sets in these types of models. Some other remote sensing data sets that we don't work on directly, but are very important to our work. Our Earth observation team produces an annual crop inventory. These are all of the different crops that are mapped every year. It uses tens of thousands of satellite data sets from both radar and optical sensors, combining it with ground data to produce this annual map. We use it to determine where different crops are grown so that we can better target our models. They're also working as part of our climate change mitigation plan, looking at things like cover crops, tillage, growth stage, grassland types, and biomass. This data set can also be used over time to look at land use change. Again, this is an important indicator for looking at changes from forest to agriculture, grassland to cropland, urbanization of agricultural land, and changes between perennial and annual crops, which are very key for estimating carbon sinks and sources. Finally, we develop a number of tools to make these data sets more accessible to our to the general public. This is an example called the Canadian Crop Metrics tool. This combines a lot of these remote sensing data sets, our yield forecasts, in an interactive tool that you can go online and drill into a specific area and make graphs of both current and historical conditions for any particular region. Finally, we use our estimates of risk to feed into a global system. So many of you might be familiar with the global crop monitoring system through the Global Group on Earth Observation. This is an initiative that's run through NASA Harvest. And we do the reporting. We use the data that we collect to produce the monthly reports for crop conditions in Canada. So to wrap it all up, our group, the National Agroclimate Information Service, leverages raw weather data and climate data to translate this into information useful for assessing risks, monitoring production, analyzing the sustainability of agriculture in Canada, which are all key tools for both mitigating and adapting to climate change. We use a station-based network in addition to satellites, model data, and crowdsourcing. These are all important tools for getting the full picture of climate-related impacts related to in agriculture. In the future, what we're really focusing on is improving the spatial temporal resolution and richness of the indicators to strengthen our ability to respond to extreme weather events as they happen. And Earth observation and integration of these data sets into models is really critical for providing this information. And finally, we try to make user-friendly tools, simplified data sets. Not everyone is a scientist, so when we put our information out to the public, we have to make sure that it's accessible to diverse user groups to allow them to interpret the information for decision making. I'll just show you again the link to our website where we keep all of our data sets and tools in visualization tools to allow people to look at them. All of this work has happened over many years with many different partners and collaborators, but I want to do a special acknowledgement to my core team in the National Agroclimate Information Service, who've been key in making all of these data sets and scientific research projects happen. So thank you very much.
Thank you very much, Catherine. Wonderful presentations. You have mentioned very broad spectrum of the remote sensing and its applications in relevance to the observational data also. So you have mentioned very important, which we are hearing that different index, based on the drought, soil moisture, and crop yield forecasting, even also optimizing the crop inventories and everything. So it's a wonderful presentations. And Catherine, we have a very learned participants who are there in the world and also from India. So a number of persons, they have worked on the remote sensing and allied sciences also. So I'll be expecting that they will be having some questions to you. So now floor is open and participant can ask question or suggestions, anything to Catherine. Over to you.
Hi, Catherine. This is Abhijit Basu from USA. I was wondering if you can summarize slide on yield forecast multi-frequency yield and suggest what are the basis points that you see that makes, other than the soil moisture and the NDVI, that makes it kind of scalable across the globe, all these trends that you see that might change.
I think a couple of words cut out there, but I think you're asking about how we're using the remote sensing for scaling up the yield estimates.
Yeah, so what I was looking at is, like, you mentioned that there is a correlation, right? Basically, you see the canola correlation with satellite, which is basically satellites are better predicting probably drought or water-stressed area production yield versus the more water resource areas. And is it specific to Canada or is it across the globe? So I want to see some of the learnings that you have from this kind of this research that you think is scalable across the globe, not specific to Canada.
Yeah, no, that's a good question. I think Canada is a good place to kind of conduct this research because we have a lot of geographic diversity in Canada. So I think the one thing that we've really taken away from this is maybe this something that works in one place is probably not going to work in another. So we have to make sure whenever we're developing any models, especially for yield, they have to be both crop specific and geography specific. So we use a machine learning model for our yield forecasting. So what we really need to do is to make sure that we train the model sufficiently in each geographic area and for each crop. And that allows us to select predictors that are specific to the conditions that are limiting yield in a particular region. So one thing we see across Canada is we have areas where the limiting factor on yield is often rainfall, but in other areas it's different things. So in our maritime regions, it's often available solar radiation. In other areas, it might be a lack of heat units, or it might be heat stress. So the one thing that we've really learned is that you can't build one model that's going to predict yield everywhere for every crop. So what we always do, and even when we're doing our drought predictions, is we don't do the same predictors for drought in one region that we would use in another, because the factors that are driving drought and dryness as well are quite geographically variable. So I guess the take-home message is, and this is where satellite data really plays an important role, is that you need to have data everywhere, and you need to customize the models to those specific regions. I find in the literature that so many models are trained over, say, the Midwestern United States, for example, and they maybe aren't going to work somewhere else because the limiting factors on yield are quite different in different areas.
A follow-up question. So as we are talking about machine learning here, so is there a possibility that you can actually train a model with another model that basically picks up all the kind of dependence data, right? Because the Earth is not uniform, and the atmosphere is not. So if we are able to create a data set of different places, different variables, and then feed that artificially created data into your model, right, to kind of set the machine learning of that model, do you think there is a scale possible?
Yeah, that's an interesting question. I'm not familiar with any particular research that's doing that, but related to that, the predictive model that's used for LAI with Sentinel data was actually trained on artificial data. So they actually ran a physics-based model to estimate all the different electromagnetic characteristics of leaves at different times of year in different regions and different frequencies, and they use that to train, once they had a data set that covered all the different variability in electromagnetic characteristics of vegetation. They actually trained the neural network, and from what I've seen, that model works quite well globally because it has been trained on such a large data set that was generated with a physics-based model. So I think that actually is a really interesting, has a lot of interesting potential to supplement in yield, because as many of you probably know, when you're doing machine learning, one of the biggest sensitivities is having enough data to train your model, and yield data in particular is very difficult to come by, especially yield data that covers all of the different variability that you see in agriculture. So even for a single field, what might be limiting yield in one year is not what's limiting it in a subsequent year. So having a rich data set is really crucial for that. And I think combining physics-based models and machine learning models has a lot of potential for that.
Perfect. I would like to take this conversation further offline, so I'll reach out to you. Thanks a lot.
Yeah, thank you. Yeah. Any other questions?
Yeah, Dr. Ramakrishnan.
Can I ask a question?
Yeah.
Namaste.
Yes.
Yeah, ma'am, I think you made a very wonderful presentation, and you showed how robust is your Agromet information network. Really wonderful, especially collecting the satellite information and soil mass estimation and other factors. One question I would like to ask is, see, when you're trying to estimate the soil mass status, you know the limitation with the satellite information is that up to 5 centimeters you are quite accurate. Fine. But generally, as the crops start growing, they go deeper. So they use the deeper moisture also. So you can't estimate a drought with that. So is there any possibility of linking these satellite information with soil mass models taken together along with the precipitation pattern? So it can assess that the drought is when it is initiating and how the drought intensity is increasing. That's one point. The second point is you are not differentiating between the crops, the grasslands, or the tree systems or forestry systems. I know forestry is a very important aspect in your ecosystem, but crops are very seasonal thing. They are hardly there for 3 to 4 months. So their pattern of growth as well as the maturity is different, and the effect of drought on them is much severe compared to the tree system, because unless there is a 3 to 4 years of continuous drought, a long period droughts, the tree system can show its impact because they are very deep rooted. So under these conditions, I think you should really link these two together. Satellite information along with soil moisture modeling. That's very important.
Yeah, no, thank you for those points. And that's exactly what we've been trying to work on with our colleagues at the Meteorological Service of Canada over the last few years, is trying to use the surface soil moisture to drive a model to get root zone soil moisture. One of the limitations that we found is a lot of the models that are used for estimating soil moisture, so models that use a very detailed Richard's equation type approach for solving soil moisture, have very poor plant water uptake functions in them. So one of the project that we just recently completed with our colleagues at the Meteorological Service of Canada was really focused on trying to improve the plant data in those models, because that evapotranspiration component was not being captured very well in the model. And although we can get root zone soil moisture that way, we're not getting a very good estimate because the model is not good enough. So I think that's one of the challenges going forward, is trying to bring hydrological models and crop models together to get better estimation of both the hydrology and the plant component. With regards to drought, yeah, we do look at crops and trees and even perennial agriculture very differently. So in Canada, because the forestry sector is so large, we actually have a different agency to look at forestry. So when we do our drought assessments, we use different indicators for forested areas than we would use for agricultural crops, because as you mentioned, they're much less dynamic, the impacts on forestry. That said, you know, the satellite soil moisture that we're using, I do provide that to some of my colleagues in our forestry service, especially in areas in Canada's north that are very vulnerable to forest fires. And they are finding that the satellite soil moisture, even though it is only an estimate of surface soil moisture, is giving a good estimate of overall dryness, which can indicate things like risks of drought, but also forest fire risk. So I think there's a lot of potential there to use it for both types of systems. But as you mentioned, they are quite different in the way that we assess drought.
Maybe linking the ground truth information also can help you to adjust your estimates in between and make corrections so that you can have better predictions in the end.
Mm-hmm. Yeah, for sure. Thank you.
Thank you.
There's another
Over to
hand raised.
Pragadash. Over to Pragadash. Can you hear me, Dr. Pragadash? Okay. Catherine, I have a small, not a question, is a query. I mean, this is challenging areas in this subcontinent that you have showed soil moisture, then deeper indexes, drought monitoring. One of the slide you have shown about that some pest you are also monitoring, you right? Okay, some crop. So here what we have the problem that we with some signature from the Centelin2 or maybe Modis, so you can identify the signature of a particular pest or disease or whatever maybe. But the most challenging things for the pest and disease is the forecasting, right? So do you have any kind of modeling that with remote sensing data with the ground truth? I mean, in combination, you can give a forecasting model for very accurate forewarning models for pest and disease. You have worked on this field. What do you?
Yeah, I haven't worked on that area as much, but we did work with our pest monitoring network the Prairie Pest Monitoring Network, who have been doing, they've been combining their ground-based surveys with meteorology data to estimate pest populations. And they actually did recently introduce a forecast. They don't use any remote sensing data at this time. We had been trying it actually using the satellite soil moisture to improve these pest population indicators and forecasts. That works is still in development. It's not clear that they're getting a much better estimate of the pest population than using traditional meteorological data, but it is an area that we're growing. I should say one of my colleagues as well, Heather McNairan, who's a research scientist at our center, she's been looking at using remote sensing data for estimating certain types of crop diseases as well. So rather than trying to detect the crop diseases directly, using estimates of moisture from radar satellites and combining that with a model to estimate things like sclerotinia, which is a fungus that affects canola crops when conditions are extremely wet. And they've had pretty good results from using that, and are working actually with the private sector right now to roll those models out. So I know directly detecting sort of leaf area damage or things like that from disease and pests is pretty challenging, because often the impacts are really localized. So it's hard to do it at kind of a national scale, but I think we've generally had better success at using the meteorology data to drive a model that's driven by ground sampling to estimate and forecast pest populations. So if you actually go to our website, our crop application actually contains a number of those pest forecasts. So I think we're up to 10 pests right now that we track through our climate-based modeling. But again, much like the crop yield, you need a different model for every single pest in every single region. Yeah. So it's complicated.
I may add a little bit information here. Some studies have been done in India using hyperspectral database for identifying these pests and diseases also, because of change of systems. Some initiation has been done.
Yeah, I think that's where there's probably a lot of promise, when we start to get more satellite-based hyperspectral sensors, that we might be able to do more with this, but those types of technologies haven't been widely available to help scale them up.
Yeah, maybe at a small experimental scale you can do for specific regions, for a specific crop. Develop these models, then you can try to expand it to or extend it to other regions.
Yeah, and I think drones can play a really important role in that kind of thing as well, to get that sort of better estimation of what's going on the ground. It's hard to cover Canada with drones. I guess much like India, it's hard to cover a large country with drones.
No, that's why I said a small area you can do an experimental basis, develop the relation, then test it at one or two places. So that can be a beginning. That's what I feel.
Yeah, for sure.
Catherine, another interesting point, which is in so many countries, even in India also, that remote sensing is used in the insurance, crop insurance, right? The insurance purposes, you have done anything? Over to you.
In the insurance, not directly. We have worked with a few partners who are, I guess there's kind of two areas where we've been involved. So things, what they call, I guess, index-based insurance. So this is, instead of looking at actual damage, having automated insurance kick in when certain climate thresholds are reached. So we have worked a little bit with the insurance industry on that. There's also been our department has sort of funded some applied research to use satellite-based indicators for looking at end of season crop losses using just simple vegetation indices. So there has been some work done on that side of thing. But from a research perspective, I haven't done a whole lot on that area.
Thank you, Catherine. Now, over to Pragadash. Over to you.
Oh, I think your microphone.
Use your microphone. Unmute the system.
Might be the button on your headset.
You unmute your system, please.
I think she's unmuted. I think it might be her microphone's turned off.
I think she can write her question in the chat.
I think you can write your question in the chat. Ma'am, you have mentioned about agro advisories in your title. How we are giving these advisories used to individual farmers or just on the national basis only, like the national drought index you have made? Is it only at the national level, or you go to individual farmers and individual regions to give these forecasts?
Yeah, with our group, we're mostly looking at the national level. Most of the work that's done at the farm level is done because we have a federal government system in Canada. Most of that work is done by our provincial partners. We do work with them quite a bit to provide them with data sets and models to help them work directly with farmers. So we provide some of our data sets and kind of custom feeds to some of our provincial partners so that they can develop systems that are more responsive to local level agricultural concerns.
Great.
Dr. Sehgal, you have worked a lot on remote sensing in India. Do you have any specific questions to Catherine?
Yeah, thank you, Navasu, for giving me the opportunity. I'm still working a lot on remote sensing, and in India, Catherine, it was really good to listen to your presentation and looking at the use of models, observation data, model data, machine learning, and remote sensing putting together to assess risk assessment and management of resources in agriculture. I have few questions, queries, and a few remarks also. Currently, I'm working as professor and principal scientist at Indian Agriculture Research Institute, and even this time I'm sitting in my office evaluating a PhD thesis. I was wondering, as you say that you are working with the soil moisture for drought, which is one of the important indicator. In India, we also evaluated different satellite-based soil moisture indices with the help of our IMD partners who supplied us with the ground observations. And we found that best among them was the modeled level 4 SMAP root zone soil moisture. The only problem is it is from 2015 onwards, so you don't get a long time series of data. But anyway, we overcome that by using machine learning algorithms to generate historical data, using many other ancillary data, including Agmera and other modeled soil moisture data, which are at much coarser spatial resolutions. And results are really fantastic. We are communicating a paper on that. And we use them to estimate, again, evapotranspir soil moisture-based indices-based drought monitoring system. So my query was that is only a surface soil moisture has worked well for Canada? Because we find it doesn't work well for India. Because we have a lot of variability in irrigation, management, dry land, rain-fed. So many issues are there. And it is not only the soil moisture and rainfall, but it is how people manage their water resources that add a very complex dimension to monitoring drought. So it is my remark, or I can say that what more we need to do. Like in India, we say that our state governments are the agencies which declare drought, and what drought declare in India is agricultural drought. Though there may be having information on meteorology and hydrology, finally how it has impacted the crops, whether the yields have reduced, to what extent they have reduced, and how much area it has resulted in prevented sowing of the crops. So do you also have some similar system where you declare the drought based on these indices?
Yeah, there's a mix of systems. We don't use our data directly. So I know in the United States, their drought monitor, if you get below a level, I can't remember if it's a D3 or a D4, it automatically triggers national insurance payments. The only system that we have for triggering a kind of a payment plan is we have a program called Livestock Tax Deferral, and we use our data sets to make recommendations on areas that should be eligible for tax deferral based on the data set. But as you mentioned, and this is what I mentioned briefly towards the end of it, we need better information, especially when you're looking at highly variable agricultural systems. And that's why we've been focusing in recent years on trying to better combine crop models and remote sensing and hydrological models. I have used the level 4 SMAP product. We did look at it for Canada. It did give very good results. The one thing we found is that the model that they're using for their level 4 was missing some things. So it wasn't giving us a lot of additional information than we were getting from the satellite data alone. And it may be because in Canada we don't have a lot of irrigation. So we're the rainfall patterns are really what's driving it. So it could be that's why we're getting better direct estimates with the satellites. But I think you're right. When we to get these sort of more specific information sets, I think we're really going to need to get finer spatial resolution, but also very much more specific information. And I think crop models are going to have a really important role to play in that. And the integration of remote sensing data sets into those types of crop models is less well developed than it is into sort of pure hydrological models.
Okay. Yeah. Anyway, you showed in a slide that you are using even Vandersat soil moisture. Also, it is 100 meter at a very high temporal frequency. I don't know how what is your experience with that. Another thing which I wanted to know, you said that Sentinel-1, Sentinel-2 LAI product, which they generate globally using artificial neural network-based model, works well with Canada. I share our experience. We worked with the same data and validated with the ground observations for wheat in India. And we found that correlation was only 0.6. So you can refer to our paper in GeoCarto International 2018, where we showed that what could be the reason and how it could be made better, and what are those specific bands which actually add information in LAI retrieval, and even what should be done. What they have used, again, a computationally more efficient way of doing atmospheric correction of the data, and we showed that if you do using a different model which is based on 6S model, how much improvement it gives in retrieval of LAI. So that is a GeoCarto international paper in 2018. Another information I wanted to know, like we have been nowadays working, as Navasu told, that this year onward, Government of India has rolled out using technology for estimating crop yield losses for crop insurance claim. So this current season rice, it has already rolled out. Yesterday, we had a minister rolling out all this scheme in a hotel in Delhi. So what we are actually doing, I didn't see that. We have developed a system where a crop model assimilates this leaf area index, and it corrects for many of the inconsistencies in data and missing observations especially related to crop management, as well as we have also designed a way to correct for the phenology based on LAI assimilation. Because in our system, all crops are not sown on one day, it is spread over 30 to 40 days. And that paper has been published in Agriculture System 2022, actually. So similar thing, you did talk of assimilation, but that was more for weather forecasting and not for crop yield forecasting. So I wanted to know if you guys are also working something on assimilating, because I saw stick model somewhere in your slide.
Yeah, that's some work that we've been doing recently, and doing. We've actually had very similar results to what you just indicated. Is that we find by assimilating the LAI data into the sticks model that we're getting a better estimation of the seeding date and the seeding density of the crops. And we were just we haven't published our work yet, but we've been working on using the soil moisture for initializing the soil moisture conditions at the start of the season as well, using sticks. So that is something that we have been looking at. And actually, your previous point as well with the Sentinel LAI product, we actually, I didn't mention that, but we have found that it does make quite a bit of difference which atmospheric correction estimation you use in terms of so that's why we actually haven't been using the Sentinel 2 product. We've been generating it ourselves based on data that we atmospherically correct ourselves. So similar experience.
Okay, and lastly, I want to thank you, and through this forum, I look forward to some exchange of ideas and some informal collaborations also, because we have similar interests and we are working on similar things in India and in Canada, because we have been working with the NDMC Nebraska, Lincoln,
Okay.
with Wardlow, with Segai. So if there is an opportunity, we can also work with Agriculture Canada also.
Yeah, absolutely.
Our knowledge and experience of smallholder farmers and using data, weather, and remote sensing. Thank you.
Yeah, we did a workshop a few years ago with some colleagues from the Remote Sensing Agency in India, because India has historically been very advanced in the use of remote sensing in agriculture, and we're a small community, the agricultural remote sensors around the world. So we have to try and learn from each other for sure.
Yeah, but I'm not from the space agency community. I'm from Indian Agricultural Research Institute.
Yes, that's even better.
Okay, thank you for your time and response.
Yeah, Dr. Saigal, actually, the intention of arranging this kind of webinar, whatever you just mentioned, because you know that the international Catherine is a executive council member of International Society for Agriculture Meteorology. This kind of agenda through this webinar, how these different countries can interact with the experts so that they can enrich themselves. Dr. Catherine, I just maybe some of them will be asked some question. Just wait for a couple of minutes. Dr. Professor Mohanty, are you with us? Professor Mohanty? Dr. Mohanty?
He's not there.
No, he is not there. Dr. Ray, you are from Canada. Yeah, do you have any question, Dr. Ray?
No, I have no question. Everything was fine. Very good, Catherine.
There was a question in the chat. Maybe I can address that.
So yeah, definitely. Yeah, right.
Okay, so considering the dynamic nature of climate change, how can remote sensing technologies and methodologies be adapted and improved to improve timely and relevant information for agricultural planning and management at different spatial and temporal scales? I mean, I think as we move into a more variable climate, all of these tools are going to be really important, because our traditional ways of predicting things might start to break down. One thing that I think remote sensing will play a role in is sort of changing normals, I guess, and because satellite data records tend to be shorter than climatological records, and that's traditionally been a disadvantage. I think the dynamic nature of remote sensing data might give us an edge in assessing things like changing normals, because we can look out over shorter baselines of time to define what is an abnormal condition than we might have traditionally done with weather station data. So I think remote sensing is going to play an important role, just because we can get more information at definitely higher spatial scales. Temporal scales remains to be seen, but definitely improving the spatial resolution will help us with planning. But I think also just in terms of defining these normals and defining how things are changing, I think satellites have an advantage, because we can look at things over somewhat shorter time scales as well, which will help with disaster response.
Any further question from anybody? If no, then profuse thanks to Catherine again for your wonderful presentation, and we will be looking forward to working with you with different parts of the world. And because remote sensing in next 10 years means everybody agreed that remote sensing and climate change will be the main issue in the agricultural field, or like that defined kind of adaptations mitigation in the high resolutions scale. And your presentation has already given the pathway that how to approach the agriculture area with a very high resolution and high accurate kind of remote sensing data and monitoring. So thank you very much for your wonderful presentations, and we'll be looking forward, right?
Yeah, thank you very much for inviting me. It was a pleasure to talk to you this morning.
Okay. Thank you. We can close it. Okay. Bye.
Thank you very